So indeed, this talk is primarily about things which are decidedly applied, but I think there is some significance of dependence on theoretical results and maybe to some extent need of theoretical results in some of this work. And I'm going to talk about the general field of learning similarity, supervised learning of similarity. I will, of course, explain what exactly I mean in the next few minutes. This is sort of work which I have been doing on and off for a few years. It was largely subject of my thesis a few years ago. And I've recently started working on this topic actively again with Ali Shapiro, who's a TI student sitting right here. And I will tell you both about sort of older work and about some of the new work, some of it essentially in progress, which we are doing. I'm quite excited about. So the notion of similarity in general is quite central to many applications or domains in computer science. Usually there are two sort of atomic operations related to similarity. One is deciding whether two instances are similar to each other or not in some meaningful sense. And the other is the goal of searching a database for examples which are similar to some input example, which we will call a query. And I make a distinction between these two operations primarily for computational reasons. So obviously, if you are really good at the first task, you could trivially solve the second task by taking your query, comparing it to each one of the examples in the database, and simply writing down the ones which are similar. The problem with that is that operation is inherently linear in the size of the database. And in many scenarios and many real-world applications, linear is just too expensive. And hence, very active area of research into sublinear time algorithms for similarity search, usually approximate in metric spaces. But because of that, this really leads to two distinct operations. I mean, you should think about them, in my opinion, as two different tasks. But of course, we would like to solve both of them. And there's this instances which we are comparing and for which we want to decide whether they're similar or not. Could be very different. Could be images. It could be instances of text. For example, we would all like to, or many of us would like to search the web for images similar to a given image. It is still something which is essentially impossible even with today's search engines. In Google Image, you can write a set of words which describe an image and look for an image that matches them. Until recently, that actually didn't even look at the image at all. It only looked at surrounding text. There is some work now on trying to find things in the image that correspond to the words. We're still quite a ways far from being able to actually give a photograph to Google and say, find photograph similar to this one. It would be nice to do things like, given a research paper, search the web for similar research papers, perhaps for us to find work related to ours if we don't already know of it, for reviewers to quickly see if there is some related work they're not familiar with, perhaps more plausibly, and God forbid for teachers to look if students have plagiarized some text off the web, and if we can do it automatically, that will be helpful. And of course, there are many others. These are just some applications I was going to immediately think of. Of course, there are many, many others. The question is what we mean by similar. And while it is easy to define similarity in terms of some geometric distance, we'll sort of get back to that point in a little bit. In general, when you look at complicated instances such as images, it is not always clear what similar means. And often there are multiple competing notions of similarity which arguably are equally relevant in different contexts. For example, if I ask you which of this, if you can find among these four pictures, two pictures that are similar to each other, what would you say? Who thinks that these two pictures are similar in some kind of meaningful way? Not many. Who thinks that these two pictures are similar? Right? So they clearly have something similar. It appears to be the same guy. It's actually a computer-generated guy, but wearing the same clothes. Seems to have lost a shoe here, but the same guy. Who thinks that these two pictures are similar? So also quite a few of you. And in fact, the application on which I work quite a bit is the application of pose estimation, trying to recover the pose of the person, sort of joint angles of the articulated body in the image. And under that, for that task, indeed, these two images are similar, and these two images are dissimilar. But if you are interested in, let's say, identifying the person, then of course I would argue that these two are similar. So what we want to do is to enable to build an algorithm, or generally methodology, to learn from examples like this. If I give you a whole bunch of images and tell you that these two are similar and these two are not, and many other pairs like this. We would like to be able to learn a mechanism which allows us to automatically predict the similarity, which is essentially task-specific, and to give you very sort of broad, with very broad strokes, the overview of how we try to achieve this. We try to essentially learn a code or representation of the images. We can think of it as just learning a bit string or binary code, which could be relatively long but not too long, that makes the underlying notion of similarity explicit. So if you and then look at these bit strings, we can think of natural comparison between bit strings in terms of Hamming distance, and then we would like images which are similar under our task-specific similarity notion to be mapped to strings which are very close to each other in Hamming space, and images which are not to be mapped to strings which are not different, not similar. So this is sort of the basic intuition, and how we achieve it technically. That's sort of the main meat of the talk. So I will tell you a little bit more precisely now how I would like to set up this problem mathematically, a little bit about some related work. It's a very active area of research, especially in the last, I would say, something like 3 or 4 years. I will tell you in some detail about the embedding technique, which I alluded to just a few seconds ago, and then talk a little bit about newer sort of new work that we are doing, which is trying to improve upon the algorithms we have developed in the past. So here is another toy example, which maybe make it the same sort of notion of task-specific linearity a little simpler and a little more crisp, perhaps. These are 2 data sets of 2-dimensional points. They're exactly the same data sets, same set of points. I think 400 points. If I draw a little red cross here in each, just again, the same position in both images, and I ask you to find examples which are similar to it, something you might do sort of naturally is to say that, well, the natural notion of similarity is Euclidean distance. You maybe will decide on some small radius, draw a little circle of that radius, a disk of the radius around the point, a query, and say anything there seem to be like 3 or 4 points falling in that disk, that's what's similar to the query. That's your answer. But what if I actually told you that I can give you a few examples of what is similar, and these are the examples? Then probably you can guess that what I really mean is that points are similar if they have similar r in polar coordinates, and then you will maybe decide that really this band, this kind of ring, is what defines similarity, and you'll maybe find a few more points. On the other hand, I can give you, for the very same data set, very same query, a very different set of examples. In this case, as you can guess, that's the radius of the polar coordinates, which defines similarity of modulo pi, and you'll get a very different, this kind of bow tie shape, which defines the regions of similarity. So we would like to be able to do this automatically by giving the algorithm a whole bunch of sets of maybe a cross and a bunch of red points for many such crosses and red points, and then discover a way to automatically predict the similarity region. Questions until now? Okay. So to make it a little more precise, there are actually a few ways to mathematically define similarity, which are all related. We are going to focus today on a very simple notion of similarity, and I would call it Boolean or binary similarity. And that means that 2 objects are either similar or not. So we have some generally unknown function s, which given 2 instances, x1 and x2, returns +1 or -1. I want to emphasize that this does not have to be transitive. That does not generally define equivalence classes. It might, in some scenarios, be transitive, but often it is not. Very generally speaking, when the similarity is related to the notion of classification, it tends to be transitive. When it's related to the notion of regression, it tends to be non-transitive. I'll talk a little more about this later. And the very common and practically important particular case of this, for example, is similarity defined as nearest neighbor relationship. So one point is similar to the other point if it is one of its near or nearest neighbors under some distance function, which you may not know directly. And we're interested sort of in a scenario where what you are given is a set of pairs of points and the similarity values. In some cases, you may be given directly the values of this unknown distance. There is quite a bit of work which is actually trying to do the second scenario a little bit less when similarity is explicitly given by Boolean notion. So this is the setup. We are not going today try to deal with a more perhaps general problem here when you are explicitly given the similarity values or distance values. There's also another notion which I should mention, which is very important and again not going to be dealt with today, and that is sort of ranking similarity. Sometimes you don't actually, what you care about is A is more similar to B than C is similar to B. There is no explicit notion of a number which you can assign to a pair of examples that they're similar this much. Only it's all relative. And that is also introduces some interesting problems, but again, not today. All right, so this is the setup. Now,
you want to talk about weighted similarity, or how we call it, when you need to assign the similarity measure comparison objects.
So I think what you're talking about is usually it's a byproduct of distance, and sometimes what you do is you say that e to the minus distance square is a similarity. So I would argue this is more like this last case, and in what I'm going to talk about today is a case where maybe you do that, but after that you threshold that and you say anything which is close enough is I consider similar. Anything which is too far I consider dissimilar. And I would argue that in many cases where similarity is used as a tool for some other computational tasks like classification, regression, machine learning, that's really what you want to do. You sort of usually can't trust the distance quite enough to heavily rely on small differences. And if something is, if your nearest neighbors are 5 inches from you, if some neighbor is 2 miles away, it's maybe okay if you think it's 10 miles away, as long as you realize it's far enough and you don't need to look at it. So I guess the major distinction which I want to emphasize here is between this work and a lot of work that people have done on unsupervised learning of similarity or distance, when you essentially have a large set of data, usually in some high-dimensional space. You assume that the data come from some inherently low-dimensional subspace. Often it's manifold. Sometimes it's particularly simple manifold, like linear subspace. If you want to do PCA, for example, that's what you're essentially assuming. And you would like to uncover this lower-dimensional subspace. And by looking at the structure of the manifold, discovering structure of manifold, and learning this distance function, which explicitly looks at the manifold and not necessarily in the entire space. A very typical example that often appears in papers which deal with this is a Swiss roll data set. Many of you may have seen it. It's a sort of two-dimensional sheet rolled into a spiral in 3D. If you think about this manifold, the meaningful distances are in the two-dimensional manifold. So if 2 points are sort of one cycle of the spiral away from each other, they're going to be very close in 3D, but in fact very far in this two-dimensional manifold. So that's not what we're doing here. We're explicitly interested in supervised similarity notion where we have specific examples of what is considered similar or not. There is also, I guess, distinction between algorithms that try to discover this sort of embed a finite set of points into another finite set of points. Perhaps the most well-known example of that is multidimensional scaling, which still solves this low-dimensional embedding problem, but also does it explicitly for a finite set of points. It basically finds a distance matrix for a given data set rather than distance function. And it's generally unclear how to extend it to points which you have never seen before. Roughly speaking, the only thing you can do rigorously is to, if you have now twice as much data as before, is to rerun your multidimensional scaling or similar algorithm again from scratch, because otherwise you don't know where to embed the new points. So we're interested in something which is explicitly functional form of embedding, which produces a computational recipe once we have trained it on our training data that we can apply directly on any new data point to embed it. And I'm going to talk about the family of Mahalanobis metrics next, because this is perhaps by far the most popular approach in the last few years to learn supervised similarity. So in general, sort of a metric which many consider to be natural metric in Euclidean space is Euclidean metric, which is the square of which is given just by dot product of a difference vector with itself. And more generally, Mahalanobis metric is the one which introduces this matrix M in the middle, which you can think of this as scaled and rotated Euclidean these days. And this is sort of a valid metric for any matrix M which is positive definite. And the idea that many people have thought of recently is to learn this matrix from examples. Typically, there is some optimization task which comes out of this, which involves minimizing the distortion between the Mahalanobis distance and the actual values of the distance function given to us. Usually it is accompanied by some sort of regularization. This term R is a function applied to M, which penalizes things like lack of sparsity, sum of the eigenvalues. So sometimes you want to encourage low dimension of this matrix. Sometimes you want to make sure that only few elements are non-zero, etc. And it's very computationally appealing form of doing this because it's usually leads to computationally tractable solutions. This often convex or easily sort of approximated very well by convex functions, solved with things like SDP, semi-definite programming. So computation is very appealing, but I would argue that in many cases it misses the mark in what we really want to achieve, at least empirically. And the reason for that is you can think of this Mahalanobis metric learning as learning an embedding of the data. That's perhaps not the most natural way to think about it, but is a sort of underlying structure. So since it's a positive semi-definite matrix, you can break it down to product of a matrix of A and its inverse, its transposition. And it turns out that this is simply, you can think of it as applying rotation and scaling defined by matrix A on your data and then simply computing Euclidean distance. So hopefully it's clear that it's equivalent. And if you think about it this way, it becomes clear that you have this linear and smooth embedding, which is why it is relatively easy to learn, but it also potentially very limited in how it can embed the data. And also, if you think about what happens when the number of data points goes to infinity, a number of data points in the database. If you look for things which are similar in this metric, you are going to eventually, as you increase the number of data points and reduce the radius which you allow, which are sort of defined by which you define similarity, you are going to get some points which are indeed similar to your to your query under almost any meaningful notion of similarity. Because asymptotically, your query, the nearest neighbor of your query under this metric will just approach the query itself, right? But the problem is with recall. You're generally going to have pretty bad recall because there are going to be, think about that polar coordinate example, there are going to be many examples which are very far under this metric, and you're not going to get them. So we are interested in being able to control precision recall, and specifically we would like to go for high recall with high precision. And this seems to be hard with this kind of learning method. So instead, what we will do is learn an embedding. So it's, in that sense, it's just like the Mahalanobis embedding, because we are learning an embedding of the data into new space. But we are going to learn it explicitly as sort of each dimension separately. And the way we are going to learn them is as nonlinear functions. So each of these functions, h1 through ht, is potentially a nonlinear function. And we are going to learn it with the objective to make the metric in the space, in the embedding space h, a good proxy for similarity, which means that once we have learned it, we would like to be able to set some threshold such that if 2 points is their targets under this embedding fall close enough to each other relative to this threshold, then we can say with high probabilities they are similar, and vice versa.
S is given, right?
Say again?
S is given.
S is given only in terms of its values on a set of points.
Of course,
Yeah. S is given to us for some subset of pairs. Yes.
Is there any particular relationship between capital T and D?
Capital T and
D. Like, is it like necessarily that?
T goes from 1 to capital T.
No, capital T and D.
Oh,
Like, is it typically?
so I don't know. That's one of the things that maybe more rigorous theoretical analysis could reveal. That I don't know. It's in general, you can argue that the more complicated is the structure of your data, is the structure of similarity in the data, the more higher numbers you need. Roughly speaking, as you increase T, if you do it sort of right way, if you just repeat the same function, it won't do anything. But if you do it right way, it's easier to separate things, right? Because you get more sort of redundant, potentially sparse representation. On the other hand, there is also, this is interesting because from computational point of view, if you are a practitioner, you want to actually use it, you would like T to be smaller because in the end, you have to do actual operations with the representation. So there is a sort of trade-off there between time it takes to search and accuracy, as in many other cases. Yeah.
Just to make sure. So in this case, it's kind of supervised learning, right? So I mean the similarity is given. So we already know that which.
That's right. That's right. Well, we know for some examples. I will get that in a second. Okay. So so let me describe how we actually learn this embedding, and let me start with an example. So let's say we are given a bunch of data points, and for some of them we are given explicit similarity constraints, right? So these pairs are told, we are told they are similar. And let's say for now that we are also given some set of dissimilarity constraints, and let's basically not worry about any point or any pair which is not one of these constraints. Let's say we essentially ignore them in learning, okay? And we'll get back to that point. So we would like to learn from this set of 4 similarity and 4 dissimilarity constraints how to partition data, and let's try to do it with 1 bit. So I'm going to build h, single function h, whose value is just 1 bit. And I'm going to do it by looking at some projection of the data. Projection is, what I mean by projection is basically any function which takes the data and returns a number, a real value number, and then you can threshold that number arbitrarily by 0. Right? Obviously, you can fold any other threshold just into f. And you get this value of h. So it returns 0 or 1. And it's actually arbitrary which side of f of this threshold that f1 is. We just decided it's on this side. So that means that geometrically here I'm showing a particularly simple case where f is a linear projection, right? So this decision is a hyperplane. It's in this case just a linear boundary. So these points happen to have value of 1. The rest of the others happen to have value 0, right? So it's just partition. Now we can look at this partition, at this 1-bit embedding, and see how well it did with respect to our constraints. And it appears that it didn't do really well. How do we compare? How do we sort of judge whether it did well or not? Well, this partition effectively imposes similarity judgment, right? 2 points are considered similar if this function h gives them the same bit. So with this kind of similarity classifier based on a function, we did not do really well because we got half of the similarity constraints wrong and half of the dissimilarity constraints wrong, right? The blue lines, we are penalized when we cut them. The red lines, we are penalized when we don't cut them. And we did kind of very badly, chance more or less. So it's not a very successful attempt. We can do better, let's say with this one. And here, what's sort of and there are a few choices that can be made here. One, which I like and decided to make, is to look at the gap between the true positive and false positive rate, rather than the 2 numbers by themselves. And partially, this is because we would like to have one value we are optimizing. So this gap is the value. So we have the true positive rate here is 1, right? All the similarity constraints are satisfied. We have 1 dissimilarity constraint violated. Right, so the false positive rate is 1/4, so we get the gap is 3/4. So that seems like a much more successful attempt to separate the data with just single 1-bit function. Now, obviously, even for this tiny toy 2-dimensional data set, that is not enough to provide really helpful embedding to judge similarity with 1 bit. So let's see if we can collect a few bits. And we're going to look at in this case, 4 bits, and we're going to look at the Hamming distance. So the first one is the one we have just looked at. And then we have a second one. And I'm not telling you how I arrived at them. I'm just sort of making some lucky guesses here. So the blue line is the next one. It happens to be pretty helpful as well. And I'm writing for each data point, I'm writing the bits which each of these functions compute for them. And then the third one, then the fourth one. So now we have embedding of each of the 2-dimensional original data points into 4-dimensional Hamming space. You can, of course, this is just an illustration. You can think of those points as images, documents, whatever else in some feature space which is given to you. Now let's look at the distance. So for this similarity constraint, we can compare the 2 points on which this similarity constraint involves. And it turns out that they actually have exactly the same binary string. So the distance between the Hamming embeddings is 0. The same is for this one. Here the distance is 1, right? Because one of the bits actually, the last one, violated that constraint. And then the fourth one is 0 as well. If we look at the dissimilarity constraint, for example, here, then we have significant difference in the bit strings. They actually differ. The Hamming distance is 3 can compute it for the others. And by just looking at this number, you see that for this particular toy case, we can set a threshold to 1, and we will get perfect reconstruction of similarity and dissimilarity constraints. Yeah.
You do care here about geometry. H must be a hyperplane, right? It's important. Or
no, this is just as part. It does not, and generally it is.
So it's a purely combinatorial program. You have this partial information, and you want to embed it into the Boolean cube, so that.
Oh, let's see if I want to perfectly reconstruct this.
What perfectly?
It might even. So I'm not sure. I mean, it could be actually unsatisfiable perfectly, right?
Of course. Yeah.
So
Unless you have sufficiently many arguments. Or rather, it will be all satisfied.
That's true. That's true. So eventually, if all of my data, I guess I can always the number of bits could be significantly higher than if it's not. But if it's not transitive,
you can get this transitive if A similar to B and B similar.
But it's not generally.
Then you can't satisfy it.
That's right. Okay. So right. So I do not actually require this the partition functions to be hyperplanes. And in general, I expect that we will do better. In fact, we do better in practice in some cases with functions which are not linear.
It's a combinatorial program, actually. It doesn't have anything about it.
Oh, yeah. The finding the optimal set of these partitions is, of course, combinatorial. Yeah. And we are not we are not trying to do that because it's clear that it's hard problem.
So do you impose any restrictions on your agents? So are they from a particular class of function?
That's right. So there is no magic. There's no free lunch or no magic bullet or however you want to phrase it. In the end, you have to specify what those functions f are, which generate h's, right? And in the end, some domain knowledge has to come into play, right? Which is domain knowledge versus computational sort of efficiency. And in general, I'm assuming that we have a guess which is good enough, which allows us to approximate the structure of similarity underlying the problem well enough with some functions we choose. So for example, I'm not going to show that anymore, but with a toy data set, it turns out that if you select linear functions, it does not work really well because specifically if you want to, if you guys remember the toy data set with radius versus angle of polar coordinates, if you want to separate things which are essentially rings in the two-dimensional space, you can do it well with linear functions. But it turns out if you go to quadratic functions, so second-degree polynomials and the two coordinates, you do really well in both of those tasks because you can approximate both the rings, well, circles, and bow tie shapes with quadratic functions. So if you guess well, you can actually do it. If you do it with linear functions, you will discover that you need hundreds of bits, even in that two-dimensional case, to do a good job. So that, to some extent, you have to work on design of those functions. But I would argue that in many cases, it's a simpler task and easier to engineer it well than to directly try to engineer similarity measure. So how do we actually do this in practice other than having lucky guesses? How do we combine multiple bits? The specific framework which we chose to do that relies on the framework called boosting. I suspect that many of you have heard of it. It's AdaBoost is perhaps the most well-known boosting algorithm, but really it's a kind of general framework for greedy approximation of, some people say greedy approximation of functions, greedy learning of ensemble classifiers. Generally speaking, it works as follows, and I'm going to show you a specific example in a minute on our problem. But the general idea is that you have some weights on the data. You start with equal weights. Then you have some algorithm which produces what's called weak classifier. All that is required to be able to do is to do better than chance on your data, bounded by some gamma away from the chance error. And the error is measured by using the weights that you have, so it's weighted error. But the first iteration of this is just a count of how many things are wrong. And once you have this weak classifier, you change the weights with the general objective, and of course it's much more precise in each of the actual boosting algorithms, to emphasize things which you got wrong and de-emphasize things which you got correct. And the idea is that the next iteration, you are going to pay more for making a mistake on an example which you already made a mistake on. So even though your weak learners are going to make presumably many mistakes because they're very simple and can't accurately solve the entire classification problem, the next iteration you're going to more focus on examples which you got wrong previous iterations. That's a very sort of simplistic, cartoonish explanation, but that's really the idea. There are specific choices of mathematical choices which make it work consistently and provide all kinds of guarantees. One useful guarantee is that boosting is guaranteed to optimize the training error. So the training error actually goes to 0 as you do more and more of these iterations. And it is actually also exhibits very good generalization performance. So what happens on test data, which you haven't seen at training time, there is still, I think, some debate as to why this is the case. There are many different people claim different explanations, which I guess is a good thing when people argue about why the algorithm is so good, rather than the other way around. So certainly, it's also attractive to me because it allows us to directly control the number of embedding, a number of bits in this embedding. So to answer someone else's question, you can directly control what's the dimension of the embedding space you get. Now, what are the weak learners here? So the weak learners, as I just said before, rely on a particular choice of function. That function is dictated by some consideration from the domain which you're working for images, text, etc. We want to maximize the gap between true positive and false positive as weighted by the current set of weights in boosting. And in order to make this actually computationally a little more tractable, we have to change our formulation from this hard threshold on which h was defined to be to a soft version, essentially by smoothing it as a sigmoid type function. And that turns it into a differentiable objective. Unfortunately, this objective is differentiable, but very clearly non-convex. And in fact, it's sort of not just slightly non-convex. As we proceed with boosting, it becomes more and more sort of crazy surface. And that is probably the weakest component of the framework I'm showing you right now, which we are trying to address to some extent with our current work. Because we know that as we proceed, we are really trapped in some grossly suboptimal local minima potentially. All right. So before I show you how boosting works in this case, I want to mention now what happens, how can we gain something from the data which are not labeled. So before we had some data points, many of the pairs were not labeled. Some data points explicitly were not labeled, did not participate in any pair at all. So they were completely ignored by the algorithm as I described it. So here is an observation which sort of informs how we treat the unlabeled data. If you think about sort of many interesting problems in the world, if you take a random 2 examples in the world, they're not going to be similar, unless your notion of similarity is kind of trivial, right? Think about 2 random images of people. If you, for example, similarity defined by either posture that I showed before or who it is or anything like that, if you randomly take 2 images from the web with extremely high probability, they are not going to be similar. And not only that, there is, in many cases, it's a very sort of rough intuition, but there is some significant structure to similar pairs of examples. We kind of can define sometimes succinctly what makes them similar. But there is very, very little structure in dissimilar examples. So my example I sometimes bring up is if you're trying to model, let's say, do face detection, and you're trying to model faces, that makes perfect sense, because faces are this interesting common structure. But it would be really strange if you tried to explicitly model non-faces, because essentially it would require you to model everything in the world except for faces in terms of visual appearance, and that's a really hard thing to do. So we can make a cavalier assumption based on this intuition. We can just say that we will just say that any pair for which we were not told that it is similar, we will just say it's dissimilar. And with high probability, in fact, we are going to be right. So this means that we can look at a complete graph, remove the edges which were labeled as similar explicitly, and then say that all the rest, which usually is going to be vast majority of the order n square pairs of examples, are dissimilar. That allows us to easily compute things like false positive rate. We just count how many edges, unmarked edges total cross this boundary, and we assume that all of them are dissimilar. And also, if we do this, then we implicitly get another component of the objective, which is that the partition must be balanced. And the reason it must be balanced is that if you make it grossly unbalanced, you are going to have lots and lots of edges which you cross. And since most of those edges are assumed to be dissimilar, you're going to do much better if you just make it more balanced. And that seems intuitively like a good objective, right? Partially, if you think about our embedding as code, you would like 2 bits to be as informative as possible. And if only 1 point out of a million has value of 1 of that bit, then it's not very informative. It has very low entropy, and that's essentially what this avoids. Questions so far?
Big O of 1 squared probably means really that you have only very, can it be
no, no, this just means the total number of, it's n times n, it just means n times n minus 1 over 2. That's total number of pairs. Minus something very small. Yeah, that's right. Good. Minus constant, essentially. And I think realistically constant. So I'm a little uncomfortable in applying this notion because asymptotic notions here are, in the end, sort of asymptotic. But I would say constant because usually labeling examples which are similar is an expensive operation. And it does not scale, I think, in most scenarios, maybe with the exception of some Google operations, things like that, which still have not become so standard. I think usually this does not scale. It is much easier to collect 1 million more images with your camera or on the web, whatever, than to label another. If you already have 1 million images and you label 10,000 pairs, it's much easier to go to collect another 1 million images than to label another 10,000 pairs. So that's sure. Or between them, it doesn't matter. Just do anything. Look at them because usually it involves, for example, someone looking at them, a person looking at them.
So in the theoretical language, we may think of your graph of similarities as something like bounded degree.
Well, it's certainly bounded degree, but I think of it as sparse. I don't know if that's theoretical language or not. Maybe we're approaching the joke stage. I don't know. So basically, I do, as far as asymptotic is concerned, I would say that I expect the number of labeled edges to be constant, maybe logarithmic, I don't know, but certainly not scale significantly sublinearly with the total number of points.
If it is constant, then you will have the problem that it will be, for example, it will be a matching, and you can easily.
That's right, but I do want to take into account all the data which are given to me, which are not labeled. And one way to think about it is that the unlabeled data, and this is common and all sort of semi-supervised. We're now turning into semi-supervised learning paradigm when we have some data which are not labeled or partially labeled. And those data provide me still with information even if they are not explicitly labeled. For example, they tell me something about the density of the data, right? Or they tell me something about the structure of local structure of similarity or local distances around various points in space. All right, so let me show you how the boosting would work. And this is a significant modification of standard boosting algorithm to take into account this unlabeled data instances. So here we have 2 sets of weights because we have 2 sets of two kinds of animals. We have the vertices of the graph, the data points, and we have the edges. So the edges are essentially what the only positive edges for now, we're assuming. Now, the positive edges are essentially what the traditional boosting sees as examples, and we are going to change the weight on them in the way which I described. If we make a mistake, we're increasing the weight. Otherwise, we're decreasing the weight, and the weights are normalized generally. And for vertices, it's a little trickier. Each vertex represents all the unlabeled edges, which you could construct by connecting it to any of the other points. And we're going to set the weights according to whether it falls on the larger or a smaller part of a partition. I'm not sure if it makes sense, but maybe it will in a sec. So let's say this is our partition. So this constraint is violated, and the other constraints are satisfied. So we are going to increase the weight of this constraint, right, and decrease the others. At the same time, there are somewhat more points on this side of the partition than on the other side. So points which fall on the larger side of the partition, their weight increases. And in the algorithm, we explicitly penalize the algorithm for putting more weight of the vertices on the same side. That means that it's now more important for us to put these points on the smaller side of the partition the next iteration. So maybe we'll do something like this. So now this guy, we got it right this time, so its weight can go down a little bit. This guy's weight goes up. These two weights on this edge and on this edge should really go down even more, and they do. Now, these 2 points have really gained a lot of weight now because they have consistently been on a larger side of the partition. And this means that they represent a lot of constraints which we assume are negative constraints, unlabeled, which we have violated. So it's really important for us to separate it. And maybe the next one will be something like this. So this weight has gone up even more, but this weight has gone down because we finally put it on this sort of smaller side. And it proceeds this way. Each time we update the weights and write down the actual partition. And by the time we're done, we have our embedding. So how can we use it? I will briefly mention some applications because I still want to talk a little bit about our new work. So I'm going to show you a few applications, primarily in computer vision because that's my main sort of field in which I'm interested, at least as an application field. And all of this, I think, all of these applications have something in common. That is the way they use computational notion of similarity as a tool to do some predictive task, classification or regression. So in general, this is part of a very generic recipe, which is nearest neighbor recipe, example-based recipe, whatever you want to call it. And the idea is that some people call it lazy learning, which seems derogatory to me, but it is in some sense lazy learning. Why is it called lazy? Because there's actually no learning at the learning time. When you are presented with training data, you just write it down. And then when you do nothing, you memorize it, nothing else. Then when you have a query or an input for which you need to predict a label, you search your database of training examples for something similar to your query. Once you find that, you look up their labels, which you wrote down during training time. And you use those labels in some usually simple way to predict a label for a query. For example, if it's classification, let's say you have some way to judge similarity between images of people's faces. You have a database of 1,000 faces, each with a name associated with the face. You have a new image of a face. You look for the image in a database most similar to your input image. Turns out that this is Sasha's face. You look up the name and report that this is Sasha. This is just one nearest neighbor classification. Maybe you do 5 nearest neighbor classification. If you have many images per person, you can take 5 nearest neighbors. Maybe 4 of them are images of Sasha's face. Then that means that by majority, you decide that is the person. In regression, if your task is to predict the value of a function on a particular query, you might do something like take 5 nearest neighbors and average their function values. And that will produce a predictor for the function value at your query. So what is common to this is the use of the operation of similarity, which I mentioned before. In this case, it is really we want to search a database and find examples similar to a query. And the 2 main problems are that we actually need to have notion of similarity which is meaningful for our predictive task. And it has to be not too expensive to search, because if it's prohibitive, even if it's an accurate similarity measure, it won't be very useful. So we try to address both of them by the embedding I described. On the one hand, we have a very clear notion of similarity, which we explicitly optimize for in learning, and that is the Hamming distance in the embedding space. On the other hand, we can use all kinds of tools for metric spaces to do efficient similarity search, KD trees, locality sensitive hashing, some other form of metric trees. You can pick and choose, but there are certainly many useful tools which allow us to do this explicitly, and which usually cannot be applied to let's say, non-metric representation. In computer vision, for example, there are many notions of similarity engineered kind of by hand, but they tend to be non-metric for various reasons. So I don't want to dwell on this. We ran it on some sort of standard machine learning benchmarks. These are not computer vision tasks. Just to see how well we do, because a lot of results are published on this. I guess just graphically, you can look at the red. So the red bar is the embedding I described. We call it boosted similarity sensitive coding. And the yellow one is the accuracy of the nearest neighbor regression using standard Euclidean distance. So lower is better. So you can see that almost in all cases wins significantly. And the blue one is the best published result, generally not necessarily using nearest neighbor at all, but using all kinds of other learning machines. And in some cases, often it's better, partially because it's just much more sophisticated regression technique. Some of them use support vector machines, for example. But in some cases, actually, it does worse than the simple nearest neighbor regression once you get the right nearest neighbor similarity.